This video focuses on applied problem solving, where rather than discussing a particular concept, we're going to apply that concept that we learned in an earlier video toward an actual example. For this problem solving session, you should first review the prior video on Lewis structures. That is video number 305. I'll go ahead and write that down here for you, that we covered Lewis structures in video number 305 of this YouTube series. And molecular geometry was from video number 303. So you can go back and look at those if you need to before we get started on this problem solving session. Let's go ahead and jump in. In this problem, we are tasked with doing two things. One, we are asked to fill in the missing lone pair electrons into the structure of serine below to give the complete Lewis structure. So in other words, what we're given here is the Lewis structure of serine minus the lone pair electrons. Remembering that a Lewis structure requires that we show all formal charges, all bonds, all atoms, and all lone pairs explicitly. We need to calculate and determine where to put lone pairs into this to yield the final Lewis structure of this particular molecule. Then secondly, we're going to label the expected geometry at all of the carbon atoms, applying VSEPR theory. So let's go ahead and begin with part A here. Thinking back to the segment where we looked at the generalities of filling lone pairs into Lewis structures, what we saw was that we can determine how many lone pairs we need to add into a skeleton like this, where we've connected all of the atoms together, by evaluating the total number of valence electrons that there must be in the Lewis structure, then from that total number subtracting how many we've already accounted for here in covalent bonds, and that will give us how many lone pairs we need to plug in. Let's go ahead and apply that. So we're going to calculate the total number of valence electrons. That's the number of electrons that are contributed to this molecular structure by each individual atom. And the number of valence electrons contributed by each atom is determined by the position of that particular atom in the periodic table. So let's take a look at the periodic table here so that we can determine this. You will have access to a periodic table if you are taking an exam or a quiz in this course or any other course. Calculating the number of valence electrons, we'll begin with our carbon atoms. Looking at the structure here, we have a grand total of 3 carbon atoms. To determine the number of valence electrons that each of those carbon atoms contributes, we look at the column of the periodic table that carbon is in. I'm numbering my columns of the periodic table right now to facilitate us in doing that. And we see here that carbon corresponds to the 4th column of the periodic table. So doing our calculation here, we have a total of 3 carbon atoms in our structure times 4 valence electrons contributed per carbon atom, since carbon is in the 4th column of the periodic table. That gives us 12 valence electrons in grand total contributed by those carbon atoms. Next in the lineup, pick whatever atom you want to do next here. I'm going to pick oxygen. I see there are 3 oxygen atoms here in this structure. And so our number of valence electrons here is going to be equal to the fact that there's 3 oxygen atoms. O there for oxygen, not 0. And each oxygen falls into the periodic table within the 6th column. And so we're going to take that times 6 electrons. So 3 times 6 makes 18 electrons in total. And with those 18 electrons in total, we'll add that to our tally of the 12 that we got from carbon. And we'll continue on down the line here, looking next at whatever atom is next in the lineup here. Finding a nice new color to use for that. We will do the nitrogen atom. Nitrogen I'm highlighting in purple, and then I will come in and use purple as my color that I do the calculation with here as well. For nitrogen, there is 1 nitrogen atom, so I'm going to put 1 in for nitrogen, and each of those nitrogen atoms, looking at our periodic table, is going to contribute 5 electrons because it's in the 5th column of the periodic table. So 1 nitrogen times 5 electrons provided per nitrogen gives us a total of 5 electrons. Now we need to sum those up and add as well the number of hydrogen atoms that we have here, because each hydrogen is going to contribute one valence electron, since hydrogen is over here on the far left in the first column of the periodic table. Going ahead and doing that, we have our grand total of 7 hydrogen atoms. So I plug in 7H for the 7 hydrogens, times 1 valence electron per hydrogen gives us 7 electrons in total. Summing that all up, the total number of valence electrons that we will need within this molecule is 7 plus 5 plus 18 plus 12, and if I'm doing the math correctly there, I believe that equals 42 electrons that we need to bring in. And those electrons are what will be found in either covalent bonds, which we've already shown here explicitly as lines, where each line represents 2 electrons in those covalent bonds, or alternatively, those can be seen as lone pairs. So we need to break this down that our valence electrons can appear in 2 different ways. One is covalent bonds, the other is as lone pairs or LPs. Now what we do next is we calculate the number of valence electrons that are in covalent bonds, because those are electrons that have already been used from this total number of valence electrons. So those are electrons that won't be available to bring in as lone pairs. So number of valence electrons in covalent bonds will count the total number of covalent bonds in this molecule and multiply it by 2, because each covalent bond brings in 2 electrons. So there's 2 covalent bonds so far that I've highlighted in yellow: 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, because we count that double bond twice. And last but not least, our 14th covalent bond there. So the number of valence electrons in total in covalent bonds, since there are 14 covalent bonds, and there's 2 electrons in each of those covalent bonds, we would take 14 times 2, giving us a grand total of 28 electrons that are in covalent bonds. Now, to determine the number of lone pair electrons, we're going to subtract the total number of valence electrons, which was 42. That's the total number that are present in the molecule as a whole, so 42 electrons, minus the number that we've already accounted for that are in covalent bonds, which was 28 electrons. So 42 minus 28 electrons, doing the math there, is going to give us a total of 14 electrons that need to be found in lone pairs. Now, how do we go about filling in those 14 electrons into lone pairs? We're going to use those primarily as our first priority to fill the octet of our atoms. And to create a stable molecule, we definitely need all of the carbons, oxygens, and nitrogens to have a complete octet. Hydrogen is our outlier. It's always going to have just 1 covalent bond to it to fill its complete valence. It doesn't follow the octet rule. So going ahead and filling in those 14 electrons, I'm going to start here at the oxygen. I notice oxygen does not have a complete octet. It instead has just 4 electrons around it right now because it has 2 covalent bonds. Each covalent bond contributes 2 electrons. So it's got 4 electrons in total, so it needs 1, 2, 3, 4 additional electrons to fill its complete octet. Now, if we were to go ahead and calculate the formal charge on that oxygen, which we definitely should be able to do, and that's something that we covered back in video number 304, calculating the formal charge on this oxygen, we would find that the formal charge is 0, so we don't need to put anything there. Just put the formal charge if there one actually exists. Filling in the octet here on the oxygen here, we need to fill in 2 sets of lone pair electrons again to get up to the octet, because we had 2 covalent bonds. That's 4 electrons in total, and then 4 more from the 2 lone pairs gives us our grand total of following the octet. Now coming over to here to this oxygen, similarly it needs 2 sets of lone pair electrons in order to get up to the octet there, and then filling the octet finally on the nitrogen down here. Nitrogen already has 3 covalent bonds, making 6 electrons in total around that. To get it up to the octet then, it needs 2 more electrons, so we'll put a lone pair on there to give the complete octet. Now, if all has gone well, we have accomplished filling the octet for all of the atoms, and we absolutely need this to equal a total of 14 electrons that we have filled in into those lone pairs. So going through and counting, I'm going to do this in pink here to highlight and help myself keep track of counting. We have 2, 4, 6, 8, 10, 12, 14 electrons in lone pairs. So that makes this number check out, indicating to us that we have successfully filled in the missing lone pair electrons, where our goal in filling those lone pair electrons in is to establish a complete octet around each atom within this molecule, other than the hydrogens, which don't follow the octet rule, and to make sure that none of these atoms have formal charges, because if they had a formal charge, it would need to be explicitly listed here in a superscript somewhere that there is a charge on an individual atom or a net charge on the molecule as a whole. So with that, we can move on to part B, where we're asked to label the expected geometry at all of the carbon atoms. I'm going to zoom in a bit here to get a more thorough view of that. And we don't really need our periodic table anymore, so I'm shuffling that off to the side here. Now, in this structure, labeling the expected geometry at all the carbon atoms, we have a total of 3 carbons here, here, and here. We determine the expected geometry, where the geometry of carbon atoms can take on 3 flavors. The 3 options here, if we were to make this multiple choice for a carbon atom, are going to be tetrahedral. Tetrahedral is where the carbon atom has 4 different regions of electron density around it, meaning 4 covalent bonds going to 4 different atoms. It can be trigonal planar, which was the case where one of the bonds to the carbon atom was a double covalent bond, and then 2 single covalent bonds, with the most efficient way to spread those electrons out being to put them in a trigonal planar shape with a bond angle of 120 degrees. And then the third possibility is linear, which is the case when you have a carbon-carbon or carbon triple bond to another atom. And the most efficient way to spread those electron regions out is to make a 180 degree bond angle or a linear shape. So let's go ahead and assign the geometry to each of the carbon atoms here. I'm going to circle the carbon atom, and then I'm going to label what its expected geometry would be. In the case of this carbon on the far right that we have circled here, counting the number of regions of electron density as 1 region going up to the oxygen, because those 2 pi bonds, or the 2 bonds here, one of which is a pi bond, count for 1 region, or 1 atom bonded. Second is coming over to here to the oxygen this way, and then third is coming this way. So this carbon in total has a total of 3 regions of electron density around, or 3 places where there are covalent bonds coming off. And so that is going to be the trigonal planar shape, where the bond angle is 120 degrees, because ideally we want to space out these 3 groups as far apart from one another as possible. So if we were drawing this in a way that's truly geometrically accurate, we would have, instead of having these lines going straight left and straight right, which is a convenient way to do it, we would have actually angled them downward to space the 3 regions of electron density, or the 3 bond angles, which I'm showing here with these green symbols. We would have had those set up so that each of those angles is identical and 120 degrees. So that's going to be our trigonal planar group there. Now, in the case of the next carbon atom over, I'm going to draw a circle around that carbon and come over here to label its geometry. It has 4 regions of electron density, 1, 2, 3, 4, because it's got 4 different groups bonded to it. And so its geometry would be expected to be tetrahedral, because spacing those 4 groups out as much as possible is going to give an ideal bond angle of 109.5 degrees and give a tetrahedral shape as those electrons repel one another. Same is going to be true at this carbon over here, which I'll go ahead and circle in purple as well. Since this carbon has 4 regions of electron density, 1, 2, 3, 4, via those 4 covalent bonds coming from it, it also would be tetrahedral. So we can assign that as tetrahedral, whereas the carbon over here on the right that had just 3 regions of electron density, or 3 atoms bonded to it, is going to be trigonal planar to space those groups as far away from one another as possible due to electron repulsion.